In this video, we're going to learn how to perform further integration of algebraic functions using substitution. Here we want to compute the integral of x times the quantity x plus 3 to the 9th power. Of course, one option is just to expand this exponentiated binomial before integrating. That would give us a polynomial, and we know how to integrate polynomials. But that would also take a lot of time, so let's try to be clever instead. Another option is to try substitution. The part that's making this integral difficult is the fact that the exponentiated expression is a binomial. If we lump all that into a single term, u, the integral might get a little bit easier. So let's let u equal x plus 3. And then we'll proceed with the regular procedure for substitution. We find du dx, that's just 1, so that means du equals dx. And we can write our integral again. It's equal to x times u to the 9th power, and then dx is the same as du. But wait a second, something looks a little bit weird. We still have an x in the integral here. When we do substitution, that's not supposed to happen. We should get our entire integral in terms of u. So we've got a little issue here. Does it spell doom for substitution? Well, no. There's actually a really simple fix here. We want to get our integral in terms of u. So why don't we just write x in terms of u? We know that u equals x plus 3, so that means x equals 3 minus u. And we can just sub that right on in for x. So this will become the integral of 3 minus u times u to the 9th, taken with respect to u. And there we go, problem solved. Now the integral is in terms of u, and we can actually integrate. Let's go ahead and multiply out this product here. Integral of 3u to the 9th minus u to the 10th du, and then we integrate and we get 3/10 u to the 10th minus 1/11 u to the 11th plus our constant c. And then we just put our answer in terms of x by substituting in x plus 3 for u. So 3/10 times x plus 3 to the 10th power minus 1/11 times x plus 3 to the 11th power plus our constant c. And there we go. We're done. We've solved it. Here's another integral for us to solve. We want to compute the integral of x squared times the square root of x minus 5 dx. Now what's making this difficult is this binomial inside of the square root. So why don't we lump this into a single term, u. So we'll let u equal x minus 5, and then we'll have that du dx equals 1, which means du equals dx. Then we have the integral of x squared times the square root of u du. Again, this integral looks a little bit weird because we've got an x there. Actually, we've got an x squared. But we can write this in terms of u by solving for x in terms of u by using the fact that u equals x minus 5. If u equals x minus 5, then x equals u plus 5. And we can just sub that into the integral. So this becomes the integral of u plus 5 squared times square root of u du. And now we can just multiply this out. U plus 5 squared becomes u squared plus 10u plus 25. And then the square root of u can be written as u to the power of 1/2. That's all taken with respect to u. So multiplying through, this becomes the integral of u to the power of 2 plus 1/2, which is 2.5, which is 5/2, and then plus 10 times u to the power of 1 plus 1/2, which is 3/2, and then plus 25 times u to the power of 1/2, all taken with respect to u. Integrating then, we have the integral of u to the 5/2. I'll just add 1 to that exponent. 5/2 plus 1 is 7/2, and then flip it, so 2/7 times u to that exponent 7/2, and then do the same thing for these other ones. So plus 10 times 2/5 u to the 5/2, plus 25 times 2/3 u to the 3/2 plus our constant c. Now we'll just simplify a little bit. This is still 2/7 u to the 7/2, but 10 times 2 is 20, divided by 5 is 4, so we have plus 4u to the 5/2, and then plus 25 times 2 is 50, then that over 3 times u to the 3/2 plus c. Lastly, we just back substitute u equals x minus 5 to get our whole answer in terms of x. So 2/7 times x minus 5 to the 7/2 plus 4 times x minus 5 to the 5/2 plus 50/3 times x minus 5 to the 3/2 plus our constant c. And there we go. We've got it. We've solved the integral. Now we know how to perform further integration of algebraic functions using substitution. And in the future, we'll continue getting a lot of practice with substitution, including with exponential, trigonometric, logarithmic, and inverse trig functions.